Hope you guys are doing okay. We want to get in and go deep into node analysis, finish it as far as current sources and voltage sources, and then move into mesh. Okay, so let's go look at the review from what we did last time, and we'll move on. So we were talking about node analysis with voltage sources. And what we said here is that when I look at node analysis, what you're going to find here is that the voltage sources and its location will tell us how we modify the node equations. So the voltage source can either be connected to the ground or it could not be connected to the ground. So then I started to look at this simple circuit right here. So we see here that there's 1, 2, 3 nodes. I'm not counting the ground. So I have 3 nodes that I have to pay attention to, the red, the blue, and the green here. So if I go look at the numbers here, I should have 3 nodes. But I noticed that there's 2 voltage sources. The 10 volt is connected to the ground. The 8 volt is not connected to the ground. So let's look at that. So if it's connected to the ground, then that tells me that that blue node must be 10 volts. So by having a voltage source connected to the ground immediately tells you what that voltage is. So that reduces the node voltages by 1. So instead of 3 nodes, we now have 3 minus 1, giving us 2 unknown nodes. So therefore, we don't know about VA, we don't know about VB. So then I look at the 8 volt source here. Now that 8 volt source sets up a special situation where VA and VB are not independent anymore. In fact, they're dependent. So what this tells us here is that how do I see this dependence on A and B? Well, if you look at just the definition, A is at the high point, B is at the low point, so therefore VA minus VB must be 8 volts. So if I rewrite this for VA, what you're seeing here is that VA has to be 8 plus VB. So if I know what VB is, it automatically fixes the value of VA. So in other words, I really don't have 2 independent variables. I only have 1 dependent variable. And so this special situation is called a supernode. And the way we identify the dependence between VA and VB is we draw a dashed loop. And that would be one thing right here. So that node cannot be considered a node for A and a node for B. It's now a supernode, which fixes A and B. So what this voltage source does then, it reduces the number of unknown nodes here. So if you go from the beginning, we started at 4 nodes minus the reference. So we typically don't even care about the reference. Then we had 3 nodes minus 1 due to the 10 volt source, and now 2 nodes minus 1 due to the 8 volt source. So there's only 1 unknown node voltage. However, every supernode requires a supercondition, and the supercondition tells us how these 2 voltage values are connected to each other. So what I want to do here is that I want to go in and I want to share a piece of my lecture notes that sort of like, the question is, how is node analysis applied with supernodes? And here I go. So what I'm going to do here is that this is straight out of my lecture notes, and I have this problem-solving strategies. So then check it out. So this is for node analysis with current and voltage sources. Step 1, choose a reference, label all the nodes, and then determine the number of unknown node equations. So here's the key. So how do I do that? the number of node equations is then going to be the number of unknown nodes. Note, I do not include the ground. And then I subtract the number of voltage sources. And that's what's going to tell you the number of unknown node equations that you must have. Step 2, then, you apply regular node analysis. Okay, you go through all of the regular nodes and you do that. So this is only for regular nodes, like we've been looking at before. And then here we go. Here's how they get modified. If a voltage source is not connected to the ground, then that voltage source forms a node, a supernode. So that means I have two nodes connected to each other. So then this is what we call the Supernode equation. And sometimes you'll see me write it like this. And then there must be a supercondition. A supercondition. So every time you have a voltage source not connected to the ground, then I can't write two separate node equations. I have to write a supernode equation. And with each supernode equation, there's a supercondition. So what I want to do here is I want to go back and I want to apply this to the circuit that we were talking about. Okay, so let's go look at the circuit here. So now here was the example that we were looking at. And I want to apply this thing. So we had a 10-volt source. Okay, so here's what our circuit looks like. And this is an 8-volt source. So then I'm going to go in here. So I'm going to go count my nodes. I got to put a reference. So what we did last time is we called this reference the ground. So then we had our nodes. Here's our 3 nodes. So then step 1 says what? So I'm going to move this here just a little bit. So then step 1 says what? It says do the numbers. Let's do the counting. And what's the counting? We want to count the number of unknown node voltages. So here I go. I don't count the ground. We clearly have the red, green, and blue. So we have 3 unknown nodes. But then I count the number of sources. I have 1 for the 10-volt source, and I have 1 for the 8-volt source. So this means I can only have 1 node equation here. Okay. So then I come in and I ask, is that node equation, because I have voltage sources, I ask, what do I know? Well, I know for a fact that this is 10 volts, as we talked about before. And then I came in and I labeled this VA and this VB. And we see that this guy here is connecting nodes A and B. So this forms our supernode right here. So what I should have done is that I should have said, okay, so what kind of node is that? Well, I know that this is a supernode. So I have 1 supernode. And so when I say I have 1 supernode, that means I'm connecting both node A and B. And then I have associated with every supernode is a supercondition, A and B, So what you're seeing here is that now I have two equations and I have two unknowns. What are my two unknowns? VA, VB. So I have two of them. So here I go. So I know that I have one supernode. So what I do now is I go to step 2, and I'm now going to apply node analysis. So I know that I have a supernode equation. And because I have a supernode equation, that means I cannot treat A and B separate from each other. I have to connect them with the supernode. So I have my supernode equation for VA, VB, and I come in and I say, let's look at that green node. If I look at that green node, I apply node analysis to that green node. So I'm going to come in. How many resistors are connected to node A? Well, I have 110, 110, VA, and then I say, how many mutuals are there? Well, there's a 10 connected to what? The 10 volt source, right? And then I have the 10 connected to the 0 volt source, and that's everything connected to what? Node A. And then in the same equation now, I got to go write the node equation for VB here. So because they're connected. So now I'm going to focus on VB. So how many resistors are connected to B? I have 10. Then I have one mutual, which will be 10 times what? 0, because that's the ground. And then if I look here, you can see here is that that's it. This is node B. So a supernode equation is writing two variables or two node equations into one supernode equation. So how many current sources do I have? 0. Okay. Associated with every supernode is a supernode condition between VA and VB. So when I look at my supernode, I could see that the high is the A, the low is the B, so it's got to be VA minus VB equals 8. That's my supernode condition. So now what am I going to do? I'm going to write it into matrix form. Okay, I'm going to write it into matrix form. So then if I go and I do this here, am I writing this correctly? Let me make sure here. Did I have? So then I'm going to go and I'm going to go look at this guy, and it's going to look like this here. So now what I'm going to do here is I'm going to write this into matrix form. So if I go and I write this into matrix form here, you could see that I'm going to have 1/10 plus 1/10 for my VA terms. And then note that I have no term for 0. Excuse me, I'm still on the first equation. How should I write this? Maybe I should do this here. I'm going to try to do something to make it a little bit easier. So I'm going to take my equation and note that this term right here is a constant. Obviously, this term is gone. That term is gone. So I'm going to take that constant term to the other side. So what you're really seeing is that you're seeing the equation VA, then I get plus 10 VB, and then I'm going to take that red 10 value term to the other side, which is going to read 1/10 times 10. That's my first equation. And then you could see here that this guy is VA minus VB, and then on the other side is 8. So when I put this into matrix form here, what you're seeing me is that I'm writing 1/10 plus 1/10, 1. Then I have 1/10 minus 1. So here's my VA terms, here's my VB terms, and then here's my constant terms. And then my constant terms on this side here is then going to be 1/10 over 10, which is of course 1. And that's my matrix. So now I have a solution through matrix magic. And then if I get my solution, I'm getting VA is equal to 6 volts. VB is equal to minus 2 volts. So I now have all of the node voltages here. So I think originally the question that I was asking, I don't remember what we were looking at. We wanted to calculate the current through, let's say, the 10 ohm resistor. So if I look at the circuit here, let me go grab that circuit. If I look at the circuit here, and I punch that into right here, what I'm going to do here is that just to give you a sense of what I'm talking about, let's calculate the current. We want to calculate current through 10 ohm resistor. And of course, there's 3 of them. So what you're seeing here is that I'm talking about this 10 ohm resistor right there. So when I'm looking at that resistor, what you're seeing here is it has a node voltage of 10 volts. And look at, we just calculated VA. So when I look at VA, we're seeing here that VA is equal to 6 volts. And this is, of course, a 10 ohm resistor. So when I go to calculate the current of this guy here, we see here that according to Ohm's law, the current of the 10 ohm resistor is going to be the voltage across that, which is going to be 10 minus 6 divided by 10 ohms. So therefore, I'm going to get 4/10 of an amp. And that's what my current is using node analysis. So that being said here, let's go do an example. So I want to go get the circuit here. And let's go do this. So this is the example that I want to do using node analysis here. So let's go do this here. So the first thing that I want to do here is that I want to be systematic in how I set this up. So let's go through step 1. So what I'm really doing in step 1 here is I need to determine the number of node equations. I can't tell you how important this is. I can't tell you how many times people go into quizzes and exams and they actually have the wrong number of equations. They either have too many or too little. Do the counting. How long is it going to take you? So that way, if you're doing the counting correctly, you know exactly what's going to happen. So where would I pick my ground? It seems like a reasonable place to put the ground here is right here at the bottom. So here's my ground. So remember, I don't count my ground. I don't count it. I count everything afterwards. So here I go. Here's my first node. My second node. And then my third node. So I see here, by identifying my nodes, I have 3 nodes. So what am I going to do here? So I have 3 nodes that are unknown. And then I count the number of voltage sources. I have one voltage source. So I have one voltage source. So therefore, I must have two unknown node equations. Okay? So let's go label them now. I'm going to go label them. I'm going to call this guy VA, VB, VC. Okay? So I know that I have three unknown node voltages. So then I ask, where is that voltage source connected? And I can see here it connects nodes B and C. So here I go. And you can see here is that this guy is connecting nodes B and C together, and therefore that's my supernode between B and C. So then I say, of those two unknown node equations, I see immediately that one of them is a regular node. So I have node A. So I have one regular node A. And then you could see here that the second equation is about supernodes. It's between supernodes B and C here. But remember, every time you connect two nodes by a supernode here, that means I need a super condition between B and C. So when I look at this thing, what I really have is that I have what? I have three equations, and I have three unknowns. And what are my unknowns? VA, VB, VC. So I better write down three equations. So let's go do that. So now I'm going to go apply my rules. Step 2. So now I'm going to do is I'm going to apply node analysis. So let's go do that. So I look at node A, and if you look at node A, there are two resistors connected to node A. I have 1 and 2, and then I have a current source that's flowing out. So let's go write this here then. You know, I think, so here I go. So I have node A. So I have two resistors. I have the 1/2 plus the 1, and that's my VA, right? There's the 2 and the 1. And then I see that the 2 is connected to VB. So then I'm going to go minus VB. And then I go here and I ask the question, is the current source coming into VA or it's going out? The fact that it's going out, then it's got to be a minus 1/2 amp. So then on the other side, I say it's minus 1/2. There's my node equation for A. Now I'm going to go to my supernode between B and C. So that means I got to write two node equations for one circuit here. So by the way, I'm going to go in and I don't like the way this is coming out. So I'm going to come in here and I'm going to get that circuit and bring it in. I don't like that I'm finding that I'm going back and forth. I don't like that. I want the circuit right here so that we can see it. Okay, here's my circuit right here. And so what we said here is that this is my red node. Here's my green node. And then here's my blue node. And we call this A, B, C. So let's do the supernode. I'm going to look at node B. And because this is a supernode, I can only write one equation for B and C. So here we go. I look at B, I see that there's two resistors connected. So it's going to be 1/2 plus 1/5 connected to B. Are there any mutuals to B? The answer is yes. There's a 2 and a 5 connected to A and C. So then I'm going to come over here and I'm going to write 1/2 VA minus 1/5 VC. So now I have everything for node B. So next, we want to go in and we want to look at the node equation for C here. So here I go. So now if I look at the blue node, I could see that there are 2 resistors. So it's going to be 1/5 plus 1/4 VC. Then I look, is there anything mutual with VC? The answer is yes. There's a 1/5 VB, and then there's that 4, but that's connected to the ground. Remember, we made this the ground earlier. So that means that 4 ohm resistor is multiplied by 0 volts, so I won't include it. So then this is my node C. So now I got to look at the current sources. How many current sources are either flowing in or out of the supernode? Well, I have the 1/2 that's flowing into the B node, so that's part of the supernode, so it's got to be 1/2 amp. And then if I look at VB, you could see that I have the 1 amp flowing into there. So I got the 1. And then if you look at node C, you could see that there's a 2. So these are all of my current sources. And if you add that, this is going to be 3.5. So that's my supernode equation. Now let's go apply the supercondition. And if I apply the supercondition, I then focus on the relationship between node B and C. You could see that C is at a higher potential than the B, so therefore this should be what? VC, VB, and what's the voltage? 2. So now I have all of my node equations. So now what am I going to do? I'm going to write this as a system of equations now. So now I want to write this as a system of equations. So that means I'm going to collect all my A's, all my B's, and all my C's. So I'm going to try to have a column for A, column for B, column for C, and a column for the constants. So here I go. I'm going to focus on my A terms, okay? I'm going to focus on my A terms. Those are my 2 A terms, so here I go. I'm going to have 1/2 plus 1. My second equation, I have minus 1/2. And then my third equation has no A, so it's got to be 0. Okay? Now let's go focus on the B terms. So if I look at the B terms, that's them right there. So now let's go write the B terms. So if I write the B terms, you can see that the first term is going to be minus 1/2 in the first equation. Then I look at the second equation. So look at this. I have 1/2 plus 1/5, and then look at that minus 1/5. So I'm going to be real careful here. Okay, that's what the second equation. Then if I look at the third one, I got minus 1. Now let's go look at the C's here. There's no C's in the first one, but there's a C here, there's a C right there, and there's a C right here. So let's go write that out. So I have 0 for the first one, and then now look at this. I have 1/5 plus 1/4 minus 1/5, and then this guy gives me 1. So I have my matrix now for VA, VB, VC. Now let's look at the constant terms. So if I look at the constant terms, I see that in the first node, I have a -1/2. The second supernode here, we see that this is 3.5. And then the second one, you know what? I should have been underlining these. So there's the 1/2, there's the 3/5, there's the 2. So then if I look at that, you could see here that the last term is then going to be 2. That's my matrix equation here. But one of the things that I want you to pay attention to is that I want you to pay attention to this guy right here. So when you look at this node equation, note that I have a 5th and a -5th right here. And when I look at VC, notice that I have a 5th and a -5th right here. So the question is, why is there cancellation of the 5 ohm resistor value? And the question looks, you got to go look at the circuit here. So let's go look at this circuit right here. And so what I'm going to do here is that if you look at the circuit, what you're seeing here is something very unusual. What's unusual is that, note that the supernode shorts out the 5 ohm resistor. In other words, the supernode, so when I look at this 5 ohm resistor here, what you're really seeing here is that this supernode has all the same supernode potential across that thing. So what it does here is that it does not physically short out the resistor, but there is a mathematical cancellation of the 5 ohm in the supernode equation. So I didn't have to include the 5 ohm resistor in my thing here. So I could have taken my node equations. Okay. I could have taken my node equations and done this thing here. I could have immediately realized that that was this one. So it would have canceled everything out. I would have just said, let's just ignore that cancellation, that number. And I get the exact same result. So I would have really come over here and just said, yep, I don't include that 5 ohm resistor because it's being shorted out by the supernode. But remember, shorted out is not a physical short. It's a mathematical short, which means that that 5 ohm value cancels out. Okay, so now that I have it in matrix form here, I now, what we wanted to do here, if you go back to the original question, the question was what? Determine the voltage and the current I. Okay, so if I'm going to determine the voltage, I want the voltage V and I want the current across the 5 ohm resistor. So now I'm going to solve. So now I'm just going to get my solution here, right? Here's my solution through matrix magic. And what we know here is if I calculate the voltage of A, I know that this is the same as V, which is 1.29 volts. So I know what that voltage is right away. So I now know what the voltage is across that 1 ohm resistor. But what about the current? Well, if you look at the current here, the current I is in parallel with the 2-volt source. In other words, when I look at this resistor here, it looks like this. Look at the picture. That's a 5 ohm. I wrote 2 ohm. Oh no, I did that right. So you could see here that I know that this node right here is what? I don't know what that node voltage is. And for that matter, I don't really care. But you can see that this guy has this value here. It has a voltage of 2 volts. So what do I know? I know that the current is then going to flow in which direction? It must flow in that direction. So this current I, according to Ohm's law here, tells me that it's got to be 2 volts divided by 5 ohms, which is, of course, 0.4 amps. Now, I have, let me see if you can hear me very, 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 very clearly. And, you know, I'm going to go back to the circuit right here. What I've learned from circuit students over 24 years, if I give you a hammer, everything looks like a hammer. Oh yeah, baby. So you want to know how big of an asshole I am? I'd give people this on, let's say, an exam, but maybe it's 8 equations, 9 equations, because you got 9 nodes that you got to solve for. And you know what people do? They'll spend 45 minutes doing this circuit. And, you know, they may get the right answer. I'd go, congratulations. But you know what they should have done? Instead of spend 45 minutes, they should have said, oh, that voltage source is in parallel to the resistor. That's the current. And then they write this answer right here, and I go, congratulations. You other dipshits that decided to not think, and everything is a hammer, so everything looks like a nail, so therefore you go in and you do the goddamn stupid shit. Think before you solve the circuit. Because guess what? It's not beyond me to do this. So think. Node is not everything. Let's go on to the next section. So now we're on mesh analysis. So being in mesh analysis here, I grew up calling it loop, so it's hard for me, okay? Mesh analysis, it's hard for me sometimes to only say mesh. You can also hear me say loop analysis too. You know, I got to tell you something that's really funny here. Is that nice one, Isaac. Yeah, it's a personal attack, I promise you. So what you find here is that I wanted to say this here. Is you know, many years ago, there was a guy who was working for a t-shirt place where they were making t-shirts. And he made me a t-shirt that had, what's that symbol that Superman wears and then, right? Doesn't he have like a big ass or something? And he made me a t-shirt that essentially called me the Supernode. When I typically do like node analysis and supernodes, I would wear that t-shirt. I didn't think about wearing it today. It's in Watsonville right now, but I thought that was a badass t-shirt. Here we go. Let's move on. So what we want to do here is that, what did we do here? What we did here is that we generated node equations using KCL. What are we going to do now? We're going to generate mesh equations using KVL. So what you want to do here is that these mesh equations generate loops or loop currents. And what we want to do is that we want to go in and we want to get an idea of what's going on. So in a very analogous way before is that we want to start off with mesh analysis. With voltage sources only. Why? It just makes it easier. And so what we want to do here is that we want to go in and we want to look at some simple circuit. So here's an example circuit. So if I look at this example circuit, I think we should start really trying to get you to start simplifying circuits here. Imagine that you have a circuit like this. You know, I realize I'm going to have to probably, nope, that's going to work. And I'm trying to make this messy. And what you're seeing here is that there's a fair number of resistors, right? So this is a 250 ohm. This guy is a 75. We have a 25. And then these are really just kind of random values, but I think it addresses a very important point. So the first thing that you should note is that if you have a circuit like this, note that things that are in series, you should reduce. In other words, because this branch is all in series, and because this branch is all in series, reduce it. In other words, we want to do some type of reduction here. So note, all of these resistors are in series. So I could write this as a 2 volt with only one resistor. And in this case, it's going to be 75 plus 25 is 100. So therefore, this guy is going to be a 350 ohm resistor. And then when you look at this other branch here, I could then go in, even though I didn't put anything, this would be a 100 ohm resistor, and this is a 4 volt. So then if I look at the branch, the green branch, you could see here that I could add the 100, 100, and 200. So I have one 400 ohm resistor, and then I come over here, and they look like this here. So there's my circuit here. So this is a much cleaner circuit than doing that. So what we're going to do here is that we're going to go through and sort of like, I'm going to go in here and I'm going to start applying KVL. So what I'm going to first do here is I'm going to identify possible loops. What I'm really looking at is I'm looking at what possible KVL loops. Now note that there are 3 possible loops, but there's really only 2 independent ones. So what we're going to see here is that there's only 2 independent loops. So how am I going to choose them? Well, typically the way I choose them here is that I just pick them kind of randomly. And what I'm going to say here is that I'm going to pick this as one of my KVL loops. and I'm going to call that loop 1. And then I'm going to pick a second loop, which looks like this, loops 2. So I have 2 independent loops. And what I have to do here is that then I have to decide on counterclockwise or, excuse me, clockwise or counterclockwise. And in this case, I chose clockwise. So now that I have that, what I'm going to do now is that it defines voltages. So what I'm going to do here is that then KVL defines polarities of the resistors. So if I look at that circuit here, look at loop 1 here. If I look at loop 1, that means if I go in this direction, I'm just going to assume that I'm hitting the positive end as I go around. But if I look at loop 2 here, note that I have plus and minus, and then here I have plus and minus. So what you're seeing here is that the red loop defines very clearly the polarity of the 350. The green loop defines very clearly the polarity of the 400. But when you look at the 100, note that there are 2 directions of polarities, one for the red and one for the green. And we'll talk about that right now. We'll have to make a choice here. So the choice that you're going to do here is that when you look at the direction of the loop, you're going to have to define which is the prominent direction. And what I'm going to do here is that I'm going to say that I'm going to make a guess. So what I'm going to do now is I'm going to make a guess and assume that when I look at the 100 ohm resistor, that when the current actually flows through this thing, it's actually moving downwards. So I'm going to say that really the polarity of the 100 is like this. So here we go. So now I'm going to apply KVL. So what I'm going to do now is that I'm going to apply KVL and convert voltages into loop currents. Okay? Via Ohm's law. So if I look at this thing, what does this really look like? Okay, so let's look at loop number 1. So I'm going to focus on loop 1. Let me see if I can get that. So here I go. So on loop 1, if I look at KVL, I'm going to start off at the 2 volt. So I'm going to get -2. Look at the next resistor here. It's 350. So I hit the plus. So I get, so it should be really the voltage of the 350 ohm. Now look what I'm coming around, then I hit the +4, and then I come along and then look at the voltage here. It's got to be the voltage across the 100 ohm resistor, and that has to equal to 0. But now I'm converting these into currents, so then this should be -2 plus 350. Now the loop current in here is going to be I1. Okay, and then I get the +4, and then I get the voltage of the 100. But note that there's 2 directions to that current here. You know what? I'm going to be coloring these guys to try to really identify what I'm talking about. So you could see that the I1 is going with what I assumed is the current through the 100. So I'm going to put plus I1, and then the green current, I2, is going in the opposite direction. So I got to put in here a minus sign. And that's my KVL loop right there. Let's go look at loop 2. And I'm going to play the exact same role here. So in this case here, I'm going to start off at the, let's say I start off at the top at the 400 ohm resistor. So you can see that at the 400 ohm resistor, I'm going to get V400. I'm going to come down. I hit the plus for the 8 volts. I come around. I hit the plus for the 100 ohm resistor, but we got to be careful here. We've already defined this to be the case for the 1 ohm resistor. So then that must be minus the voltage across the 100 ohm resistor, because I can't have it two different ways. And then I come up, I hit the negative of the 4, and then of course that's 0. So what am I going to do here? I'm going to convert everything to currents. So the 400 I could see is going to be 400 times I2, and then I get the 8. And now let's look at that 100. We know that that's 100, but we already defined that this was I1 and this was I2, as we already did before. And then I get the minus 4, and then this is 0. So what are you seeing here? What you're seeing here is that this is mesh analysis right here. You apply KVL and then convert them into these equations here. But wait a minute. There's a mathematical trick. And what we want to do here is that note this is not in matrix form. So you still have to put this into matrix form. So what we want to do here is that we want to go back and we want to look at this equation again. So I'm going to take this guy and I want to bring it down with me. What I want you to realize here is that I can do the algebra right here. So look at loop 1 right here. If I take loop 1, look how I can combine the reds. So if I combine the reds, I get 350 plus 100 times I1. Look at the green. I'm going to get minus 100 times I2. And then look at my sources here. I'm going to bring the 2 to the other side and then the 4 to the other side. So I'm going to get 2 minus 4. So that's the algebra. This is associated with loop 1. So check this out. Look how I'm doing my KVL loop here. Note that these resistors are what? They're connected to loop 1, right? There's the 350, there's the 100. Look at the 100 now. What's special about the 100? It's a mutual resistor between loop 1 and loop 2. So if I add all of the mutual resistors, all of the resistors connected to loop 1, I automatically get 350 and 100. But if I see a mutual one, I subtract it. Now let's go to loop 2 here now. So if I go to this circuit, look what it says here. For loop 2, if I play the same type of game here, look at that. I have 400 and 100 connected to loop 2. And then I ask, is there a mutual resistor between 2 and 1? The answer is yes, which is the 100. And then, of course, that's the mutual current in that resistor. And so what you're seeing here is that if you were to look at equation 2, look how they added up. I got the 400, then I got the minus 100, and then it canceled with the minus with the I2. which gives me 400, 100. And then I get a minus 100 that's red, which is right here. So you can get the same type of thinking, but what ends up happening is you get it into matrix form right away. This is everything connected to loop 2. This guy's going to be what? A mutual resistor. And my job here is to try to set you up in such a way that I reduce your number of mistakes when you start writing down these equations. So now let's deal with the sources here. So the way I think about this is that let's look at loop 1. Look at the source. So as I go around in the red loop, I have a minus 2. But up here, where's that minus 2 at? The minus 2 is right here. And then I come around and I hit the plus 4. So where's the plus 4? Right there. So what do? So in my head here, I sum all of the resistors connected to loop 1. I subtract the mutual ones. And then in my head, I say here, I see a minus sign. I take the 2-volt resistor of source to the other side, and it becomes what? Plus 2. When I come to the 4, I know that that's a plus, but when I take it over to the other side of the equation, that becomes a minus 4. So look at loop 2 now. As I come around the loop, what am I seeing here? I'm going to hit the 8, but the 8 is what? Negative when I take it to the other side. So then I write negative 8. So therefore, you're seeing that this positive 8 on the left side becomes negative 8 on the other side. And then I come all the way around. I hit a negative 4. And then what do I do to the negative 4? I take it to the other side, and it becomes a positive 4. So I have a way of rewriting these mesh equations like this here. So when I talk about my sign convention, right? So for sources on the other side of equation. So you got to be careful. I'm still thinking KVL. So here's what I see. So if I have a voltage source, it looks like this. So if I look at the direction of the current's coming in this way. Okay, that's my loop current. And when I look at this thing, that means on the other side, I write a minus Vs for the voltage source. If I have a current that's entering in the minus sign here, then when I take it to the other side, I'm going to get a plus Vs in the equation. So if that's the case here, then what I can do then is I could come in, and I can then come in and write mesh analysis here. And I'm going to write it using my trick here. So let's go do this. So it looks something like this here. So I'm going to write mesh analysis with voltage sources only. So let's go look at that. So here we go. Step 1. Step 1 reads, for each loop, right? For each loop, assign a loop current and determine the number of unknown loop currents. And what we find here is that this tells us here that the number of loop equations is then going to be equal to the number of unknown loop currents. And again, counting becomes super important in node and mesh. So then here's step 2. So step 2 says, apply the loop equation to each unknown loop current. So then you have to apply the loop equation to each unknown loop current. So if I do that, it's going to go like this here. So it should be the sum of resistors connected to loop 1 times that loop current minus the sum of mutual resistors connected to mutual loops, however many they may be. And then following our sign convention, then it's going to be plus or minus the voltage source. So this is what I call the loop equation. So for example, if I have 2 unknown loop currents, then I have to write down 2 loop equations for each loop. And so then next I come in, I then go ahead and I solve for all the loop currents and appropriate variables. That is mesh analysis right there. Okay. So what I'd like to do here is that I want to come in and I want to practice this with you, and I want to go in and look at the next circuit.
Question?
Yes.
So you set up the matrix columns based on one column is mutual resistors?
No, they're
Okay.
based on not mutual resistors, they're based on loop currents. So,
okay, so you would have one column for I1, one column for I2.
Yes, that is correct.
Okay, okay. So you just never actually finished setting up the matrix above?
Oh, we will.
Yeah, gotcha.
Because we'll have sources in there. So let's go practice on this example right here. So there's lots of ways that you could create these loops. In fact, there are 6 possible loops right here. But what we're going to find here is that we want the most obvious loops. Okay. And when I look at just the surface of this thing, there are 3 possible loops. But there's really, there are 6 possible loops. 3 of them are the ones that make the most sense. Could I pick other ones other than the ones that seem pretty obvious? Yes, but you'll see it makes your algebra, when you go to the problem solving, more challenging. So what we want to do here is that we want to define 3 mesh currents or 3 loop currents. And so let's go do this here. So what I do here in the first step, right, in step 1, what I'm going to go do here is that I need to count the number of unknown loops. And when we look at this, we can clearly see that there is 3. So I'm going to come in here and I'm going to do the following thing. I'm going to say, okay, here's my loop 1, here's my loop 2, and here's my loop 3. So this tells me then that I have 3 unknown loop currents. So that means I must generate 3 loop equations. So I know what those are. And these 3 loop equations are going to involve what? I1, I2, I3. Such a simple thing to do, but some of you are going to get very, very confident in what you're doing. And I just want to let you know that as the problems get harder, and they will, by the way, I promise you, you're going to find that if you're not careful with how you set stuff up, it can really come back and bite you in the ass later. So just how long did that take, right? This is a simple one, but it doesn't take that long to actually do that. And all you're doing is protecting yourself. So what you're seeing here is that I have 3 loops right now, but then look what they're asking for us to solve. We want to solve for the voltage across the 3 ohm resistor. So the question is, clearly we only have one 3 ohm resistor. So now what I'm going to start to do here is that now I am adding a solver equation. What I'm doing here is that when you look at the voltage across the 3 ohm resistor, that's something that's being asked, right? They're asking, calculate the voltage across the 3 ohm resistor. So what I'm going to do here is that I have to make an assumption here. And the assumption is, what is the polarity of that 3 ohm resistor? And I'm going to make a guess. So I'm going to come in here and I'm going to say that the polarity of this 3 ohm resistor is going like this. Could I have picked it the other way? Absolutely yes. So what you're seeing here is that I'm saying that this guy is my 3 ohm resistor. So let's look at that thing. So what I want to do here is that we want to write the voltage across the 3 ohm in terms of loop currents. So what does that look like? Well, let's look at this thing here. I have a 3 ohm resistor. And I already said that this was the polarity of the 3 ohm resistor right there, right? But now let's look at the 2 loop currents here. Look at I1. I1 is going where? It's entering the positive terminal. Look at I2 as it comes around. It's entering the negative terminal. So what this tells me here is that according to Ohm's law, I know that the voltage across the 3 ohm must be the resistance of the 3 ohm times the current of the 3 ohm resistor. So this tells me here is that I can rewrite that 3 ohm resistor as what? 3, then I1 hits the positive one, so that goes first. I2 is negative because it's in the opposite direction. So that means then I now have written my 3 ohm resistor in terms of loop currents here. So what I'm saying here is that this now is my voltage written in terms of here. However, this is not in matrix form, right? This is not in matrix form. But you know what? Before I say that, let me be careful here. That's not really where I want to go with right now. This process adds a new variable to solve for in the matrix process. So what I'm really saying is that I'm saying this here. I asked the question, how many unknowns? So what's the number of unknowns? In this case, we see that I have I1, I2, I3, and now we add in a solver, which is V3 ohm. So what this means here is this tells me that I need 3 loop equations for I1, I2, I3, and then I have 1 solver equation for V3 ohm. So then that tells me that I have 4 unknown, 4 equations. So I need 4 equations, and I need for my 4 unknowns. So immediately what you're seeing here is that I must have a 4x4 matrix to solve this system of equations. So what am I going to go do? I'm going to go solve this circuit here. So let me go up and grab this guy, and I want to take this with me. No, I don't. I want it down here. So here's my circuit. Okay. I think I'm going to put it over here because I ran out of space last time. So here I go. So what I said here is that I had loop 1, loop 2, loop 3. And then I had my polarity on this guy to get the voltage. So here I go. So here's my loop 1. So look at my loop 1 now. How many resistors do I have connected to loop 1? I got 2, 9, and 3. So I go 2 plus 9 plus 3, I1. How many mutual resistors are there? Well, look at, there's the 3 connected between 1 and 2. So I'm going to write 3 times I2. Look at the 9, it's connected with 3. So it's got to be minus 9 I3. Now, how many sources are connected to loop 1? 0. No sources. Let's go to loop 2. So now I'm focusing on loop 2. How many resistors are connected to loop 2? I got 3 and 6. So here I go. 3 plus 6, I2. How many are mutual? I got 1, which is connected to 3. So I got 3I1. And then look at the 6 is connected to loop 3. So I got minus 6I3. And then how many sources do I have in loop 2? You could see 1. Look at my direction of my loop. I hit the plus, so I got plus 15, but then I got to take it to the other side of the equation, which then gives me minus 15. Loop 3. How many resistors are connected to loop 3? There's 9. There's 2. So I got 6 plus 9 times I3. Now I'm looking at mutuals. I got 9 with loop 1, 6 with loop 2, and then I look at the sources. How many sources are connected to loop 3? There's only one, but look at the direction of my loop 3. As I come in, it hits the negative. What do? I take the negative to the other side of the equal sign, and it gives me plus 21. So then I have my solver equation. So what was my solver equation? Remember how we wrote that? We wrote that as 3 ohms. I see that the 1 hits the positive sign, so it's going to be 3I1 minus I2, and those are my 4 equations now. Okay, so I generated 4 equations for 4 unknowns. Let's go matrix this guy up now. So if I'm going to matrix this guy up, what does it look like? Well, I'm going to set up my I1, I2, I3, V3, and then my constants. So here I go. I'm going to focus on I1. Everywhere I see I1, I got to add it in. So then I come in and I go, it's 2 plus 9 plus 3. Equation 2 is minus 3. Equation 3 gives me minus 1. And look at this guy here. I got 3 here. But you know what? This is not in matrix form. So maybe I should have written this like this here. This is the equation I should have written. Look at, I rewrote that into matrix form. Okay, there's my 4. So now I'm going to go after my I2s. Right? So here I go. I2 is then going to be minus 3, 3 plus 6, minus 6, and then finally minus 3. Then I go to my 3s. And there's nothing in the last one. So then I come in and I start adding them. For 3, I'm going to see minus 9, minus 6, and then this is going to be 6 plus 9. And then there's 0 I3 in the solver equation. Look at V3. The hint about V3, you know it only applies in the last equation. So this should be 0, 0, 0. And you could see that I only have one V3 here. So in this case, it's minus 1. Now let's look at my constants. When I look at my constants, you could see that I got 0, this, and that. So then I'm just going to write them in. So I'm going to go 0, minus 15, 21, 0. I now have set up my matrix equation here. So what I'm going to do, I'm going to solve them. I punch this into my matrix solver, and I'm going to get solutions via matrix magic. So what do I get? I get a solution for I1, I2, I3, V3 ohms. And what do I get? I get that the first current here is going to be 3 amps, 2 amps, 4 amps, 3 volts. These are my solutions right here.
Question?
Yes.
Does this work if you have not the same rotation for each loop?
It does not work.
Right. So you need this. You've chosen clockwise, but I could have equally chosen counterclockwise.
Yes, and if
that
you had,
wouldn't work. And it's essential.
Yeah, I don't recommend you also. You could have changed the direction of loop 2. Then you can't blindly go in and add and subtract, add resistors to the loop with mutual resistors and stuff like that. You would have to really go in and pay attention to signs. And there are a small percentage of students, very small, maybe, a few percent, but that's what you find here. So before we finish, let's look at this thing here. So note, V3 ohm is positive 3 volts. That tells me that the polarity of the 3 ohm resistor is literally as shown. It's 3 volts. If one had a negative value, remember, this is an assumption. In other words, that you calculate 3 ohms, let me call that prime, you got 3 volts that were with a negative sign, then that just tells you that the polarity changed and it's really this way. Okay, but note that's not our case. This is just an example. And the other thing is that, let's say we wanted to calculate the current of the 6 ohm resistor. So if you're looking at the 6 ohm resistor, and I got to get out of here, and I apologize that I'm going over by a little bit. What you're seeing here is that I have 2 currents. Note that 2 is coming down and 3 is going up. So in other words, I have I2 going this way, but at the same time, I have I3 going this way. So look at the currents here. This guy is 4 ohms. The 2 is what? 2 amps. So what you're seeing here is that the actual current through the resistor should then have what? A polarity of plus or minus. Why? Because look at the higher current is going to force it up. So what you're seeing here is that the current is actually going in this direction right there. And it should be 4 minus 2. So I know that's 2 amps. So what's the voltage of that guy? That guy has a voltage of 12 volts. So that's how you would use loop currents to calculate voltages across resistors. Okay, I'm over by 1 minute. My apologies. I will see you guys tomorrow in lab. Otherwise, I'll see you on Wednesday. Okay, take care.
Thank you, Carl.
You're welcome.